All right. Good morning, everyone. I hope you had a good weekend. So let's see the usual reminders. So homework number 3 will be due on Friday at midnight. Lab and tutorials start this week, so show up to whatever sections you're registered in. There's no pre-lab for lab 0. There is, however, a pre-lab for lab number 1. And what I wanted to do is I just wanted to start by just taking a couple of minutes to show you how you would do your pre-lab. And in fact, this will also be some tips on how you'll start your actual lab when you show up. So when you log into Canvas, what you should find is you should find a shell that's called Physics 121 Labs 2023 W2 for winter term, term 2. And so you just click on that. I'll go into student view. So what you see should look something like this. And then you would just go into modules. All right. And then lab 0 is you'll use these materials for lab 0 this week. I'm going to open the pre-lab just to because that's something you're going to have to do on your own at home. So for the pre-lab, you would go down to lab 1, and so they've published the links to the pre-lab, and so you would find this default link. If the default link somehow doesn't work for any reason, there's like a backup one. So you just go to the default link and you click on it. It forces you to click on another link. So we'll just click on that. And it should open a new tab in your browser, and it'll open the pre-lab for you. And it'll look something like this. So I'm not going to do this whole pre-lab in front of you, but I'll show you kind of the steps that you would complete in order to make this work. All right, and so when it opens up, you'll see something like this. So this thing's a Jupyter notebook. And what it's got is it's got some notes for you, and then it has some what are called cells where you're going to type in whatever response is required. So this first cell, it just says this is pre-lab number 1. It's out of 8 marks. And the topic is going to be simple pendulum. And the other thing that I'll mention is that we've tested that everything that we have in these labs and pre-labs works well for a Chrome and a Firefox browser. That doesn't mean it doesn't work in other browsers, but those are 2 that we've tried. And so I recommend that you try these things. Okay, try those browsers. And then if you scroll down, there's some learning objectives, there's some more notes, and then you'll eventually get to some of these cells that look gray. These are cells that have commands or little chunks of code that you can execute. The way that you execute a cell is you put your cursor in there, and then you hold down the shift button and then hit enter. And then you'll see you got like a little star in here. So that star means that whatever is happening, that cell is currently executing. And then eventually it turns into a number. And once the number appears, so it says number 1, that means that's just the first cell I have executed. The star is gone, so it's completed doing whatever its task was. The task of this one was to install some packages that you'll use for your pre-lab. And if you read these notes, it says, if it says that it has installed some packages, you should run the cell a second time. So what I'm going to do is I'm going to put my cursor in there, and I'm going to hold shift, hit enter. And this time when it runs, it says packages already installed, please proceed. Okay. And so whenever you see a gray cell, you can just hit shift enter. This one is called Otter. It's just a package that we're going to use to help grade some of the responses that you enter into these notebooks. Okay, and then there's some modules that we'll use, Shift Enter. All of this stuff is just preamble to actually getting to the lab. And then there's a bunch of notes. What tends to happen is students don't read the notes carefully. And so I recommend that you do read the notes rather than just going through and hitting Shift Enter as fast as you can, because you're not going to get anything out of this if you don't take any time to read the notes and figure out what we're trying to convey. So take some time and read the notes. And then here's another code cell. And what it's going to do is it's going to generate some simulated data and then plot it for you. Okay, so here's 20 data points that it generated. And then what we're going to do is make the plot. And it makes a plot of a histogram of the data. And you just keep going. And then eventually, what you'll do is you'll get to a question where it says, in 2 or 3 sentences, comment on the shape of the histogram that was generated. And to answer that question, what you would do is just read this line. It says, double click this cell and enter your text here. So we just double click and it says you may delete all of this text when entering your answer. So you delete all of this and then you just type in whatever your answer is. So this is my answer. And when you're done, you just hit Shift Enter. And that's the answer that will be recorded. And that's the stuff that your TA will read and grade. Okay, I'll show you one other type of question here. We've generated another plot. What this plot is showing is those 20 random data points that were produced. And it's showing the average of those data points. That's the pink dashed line in the middle. And then it's showing the average plus the standard deviation. That's the red line. And it's showing the average minus the standard deviation. That's the blue line. And what we're supposed to see is how many of these data points fall between the red and blue lines. And so if we count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I counted right, I think it's 12. Okay. Now, here's a question that says, replace it with the fraction or decimal of the number of data points that are between the mean plus the standard deviation and the mean minus the standard deviation. And so your questions will always look something like this. And what you have to do is you delete those 3 dots and then enter your answer. I'm supposed to enter a fraction, and it's 12 out of 20. What I'm going to do is I'm going to enter a wrong answer first. So I'm going to put 10 out of 20 and do Shift Enter. And then below it, there's this greater dot check. And what it's going to do is it's going to tell you, it's going to give you some feedback as to whether or not you've correctly answered this question. And all right, so we get some messages here, and it says that we got something wrong, and the message is try again, count the number of points between the red and blue lines. Okay, I think it was 12. So what I'm going to do is I'm going to go back and I'm put 12, and then I'll run this greater check again, Shift plus Enter, and it says passed. Okay, and you can try these questions as many times as you want. The only thing that will be graded is the last response you put in there. And so if it says passed, then you can be confident that you've done something correctly. Okay, I'm just going to skip through the rest of this. You can do this on your own time, but I want to show you how you're going to do the feedback. So feedback and submission. At the end of the lab or the pre-lab, there's always going to be this little cell where you can type in whatever feedback you want, what you liked about the lab, what you didn't like about the lab, anything you like. That's not graded. That's just information for us to try to help improve the lab. If you don't want to put any feedback, that's fine. Then just before the submission, there's our grader dot check all. It's just going to recheck all of the solutions that you've entered, and you'd like it to say that you've passed everything. Okay. And then there's a submission. Now, this is important. When you do your submission, you have to save the notebook first. If you don't save it first, it will automatically save, like maybe every couple of minutes. But if you do the submission without saving, all of the stuff you did after the last time it was auto-saved will be lost. So you just go up to this little floppy disk here, and you just save it. Okay, so you just save it, save it, save it. And then you can hit Shift Enter in this grader.export cell. The little star means it's running. This will take a second to run, and there we go. So what it's done is it's created a link here. It's a zip file that contains everything that you're going to submit for your pre-lab or lab. And so you just click on here, and it downloads for you. Oh, here, let me see if I can find it. So download, so this one. So it downloads a zip file. All you have to do is upload that exact zip file to Canvas. You don't need to go into it and change anything. You don't need to change the file name. Just leave it exactly the way it is and submit that. Okay, and so what we would do is we'd go back into Canvas. We'll go to, let's say, grades. Let's go into assignments. And so I'll go to pre-lab 1. Okay, so then choose my file. I'll just go into the downloads folder. Where is it? Here it is, downloads. Grab that zip file and then just submit. I don't change anything about what I downloaded from the notebook, and then confetti. So what you want to see is that confetti, and that's it. So that's how you're going to run the labs and the pre-labs. Okay. Any questions about this? Yeah. Yeah. So there will be, the pre-labs might be like a mix of some of these auto-graded questions that will be checked like while you're doing it, and then also some possibly some answers that you type in. So you'll be graded on those things. Yeah. Anything else? All right, good. Okay, so before we go back to the tablet, let me show you one other thing on the course website this time. So course website, I updated a couple of things last night. And one of them is that we're going to have our first quiz on Wednesday, January 31st. So that's Wednesday of next week. And I've put some information about the quiz here on the website. So first of all, it's going to cover sections 5.1 to 5.6 of the textbook. And I think essentially what we will reach the cutoff for the quiz after today's class, okay? There is a formula sheet, and so that formula sheet is, you can just download a PDF of it, and then it's just got some formulas related to the material that we've been working on. And so it has some stuff, like it has some constants in here. It's got the kinematic equations for constant acceleration. It has the angular frequency of the pendulum. And then it's got like Coulomb's law, the electric field of a point charge, the electric field of a line of charge, electric field of a ring of charge, which is something that we'll do today. Okay, and so when you're doing the quiz, you can print out a copy of this formula sheet and have it with you. But There's no other resources, no textbook, no notes, no searching for things online, that kind of stuff. The quiz will be on Prairie Learn, and you don't need to come to class to do it. You can just go wherever you want, wherever you can kind of sit in a quiet place with your own laptop and just complete this online quiz. Although you don't need to come to class, the quiz will run during class time. Once you start it, you'll have 40 minutes to complete it. So it will open at 10 o'clock and it will close at 11. So if you want the full 40 minutes, you have to start the quiz by 11:20. If you start it after 11:20, you'll just have whatever time's left. Sorry, did I say 11:20? You have to start it by 10:20. And then 40 minutes later would be 11 o'clock, and that's when it's going to close. If you start the quiz at 11:30, then you'll automatically have only 30 minutes to do it. Yeah. I will be here. So if you want to write the quiz here, you can do that, but you still have to bring your own device so that you can complete it. What I'll do is I'll start a Zoom session, but I'm not going to do anything. I'm just going to be sitting there. And if people want to be in that Zoom session, they can ask questions via the chat. And so you would send me a direct message in the chat and I'll respond to it as quickly as I can. Okay. It's multiple choice questions. There's going to be 10 to 12 of them. So 10, 11, or 12. And you'll have that 40 minutes. If you're registered with the DRC, then you will get whatever extra time the DRC letter says. So if you have time and a half, you would have a 60-minute window to complete the quiz instead of the 40 minutes. All right. The only other thing I'll say is that you have to do this quiz independently. Anybody caught working like collaboratively in a group or talking to anyone like over text or whatever, or searching for things online, any incidents like that that come to light will just be referred directly to the dean's office. I'm not going to do any investigation. I'm just going to pass the information along. Okay. Good. Any other questions about any of that? Yeah. Yep. Yeah, just the formula sheet you can have. And you can have a calculator. So whatever calculator you like, graphing calculators are fine. Okay, good. So let's go back to the Zoom thing. And let's see, I think I just got to log back in here. Okay. And then I have to share my screen again, I guess. Share screen. Okay, good. So now I think we're back in business. All right. So then what I want to do for today is I want to finish off what we're going to talk about for making electric fields from continuous charge distributions. We did one example last time, and it was the infinite line of charge. And remember, the way we thought about doing this is by selecting a particular piece of the rod, figuring out what its charge was. Say delta Q is going to be the charge per unit length times, say, delta X, where delta X is the size of the chunk of rod that we picked. And so we could treat that little tiny piece of the rod as a point charge, and we could say, well, it makes some electric field at point P that points, at some funny angle. But then there's another point charge that's placed symmetrically on the other side, say somewhere over here, that makes a similar electric field that points in such a way that the x components are going to cancel, and we'll only get the vertical components of the electric field. So what we did is we said, okay, let's find the vertical component of the electric field due to the piece of rod of length delta x. And then we're going to add up the contributions from all the little pieces that are needed to make that rod. It turned out that we could express that as an integral, and then we wrote down this final result, the electric field due to a uniformly charged long rod is lambda, the charge per unit length, divided by 2 pi epsilon naught, bunch of constants, times r, the distance away from the rod. Okay, so what I want to do today is to do a similar kind of calculation, and I want to show you that a lot of the results that we already have can just carry over to this other problem. So I want to think about a ring. So this is going to be some ring that has been charged. And it's charged uniformly. So that means the distribution of charge is, or the density of charge at any point on the ring is the same as the density of the charge at any other point on the ring. All right, let's draw a coordinate system. So this will be, let's say, my z-axis. This will be my y-axis, and then over here will be my x-axis. Okay, so what our task is to find the electric field at a point along the z-axis due to the uniformly charged ring. Okay, so let's draw our point P. So point P is going to be over here. All right, so first question is, what direction is the electric field at point P going to be? Up, down, left, right? Let's make this ring charged negatively. So what direction would the electric field be at point P? Down, right? So again, it's a symmetry argument, very much like we made for our charge line. So let's do this. Let's assume that the ring has a negative charge. Let's say Q ring is less than 0. So Q ring is some number that's a negative number. And so in that case, the charge per unit length is going to be lambda, is going to be Q ring divided by the length of the ring. And because it's a circle, that length is a circumference. And so it's just 2 pi divided by the radius. And so over here, we'll label this as the radius r. And then let's label this height z. Okay, so then by symmetry, like if I pick a piece of the ring that's on the y-axis, like a positive y value, then it's going to make some electric field that, let's pick a piece of charge here, and we'll call this delta Q, and it's going to make an electric field, say delta E, that points to this. So delta E is the contribution of the electric field due to just that delta Q. And because our charge is negative, electric fields point towards the negative charges. All right, and then we can label this angle as theta. But I could likewise pick a delta Q that's at some negative y value on the y-axis, and it's going to make an electric field that points towards it, and the horizontal components cancel, and we're left with just the vertical components. So by symmetry, the net electric field will point along the negative z axis. All right. So what we could do is we could draw that component of our electric field. And so this would be delta E times cosine of theta. Okay, good. So what we have then is, let's draw some of this geometry again. So we've got our point P over here. This is our Z height. And then we have a radius R. And then we've got the hypotenuse of a right angle triangle. This is theta. And here we have delta E. And then here we have delta E cos theta. The hypotenuse of our right angle triangle has a length of z squared plus r squared. And so cos theta is the adjacent side divided by hypotenuse is z square root of z squared plus r squared. And if you look back from our notes last week, we had this exact same expression for cos theta when we were doing the line of charge. Okay, so then the delta E, let's say the Z component is going to be delta E cos theta. Well, delta E is the electric field due to the small point charge delta Q. But we know that for a point charge, the electric field is Coulomb's constant times the charge divided by the square of the distance from the charge to our point P. And so this is going to be our delta E. And then our cos theta is Z square root Z squared plus R squared. And this is our cos theta factor. So that our delta E Z component is going to be Coulomb's constant delta Q times Z divided by Z squared plus R squared to the 3/2 power. All right. So what we would do then is to find the net electric field is we would add all of these contributions up for every one of the little point charges around our circle. So E net is going to be the sum of all of these contributions for all point charges on our circle, or let's say on our ring. Okay, so we're almost done, but before going a little bit further, what I want to do is I want to see if we can find an expression for this delta Q. And so we're going to do a top view of our ring. Okay, so what does it look like? This is our ring, something like that. And then what we have is, I'm going to exaggerate it so that it's easier to draw. So what we're doing is we're considering this section of the charged ring. And so I'll call that delta Q. And let's call this angle that defines this little green arc as phi. In fact, I'll call it delta phi. Let's do that, delta phi. I'm not using theta because we've already used theta for the angle between our z-axis and that electric field delta E that we called it. Okay, so remind me, if our circle has radius r, what is the length of this arc? How do you calculate the length of an arc for a piece of circle? It's radius times what? This delta phi, exactly, right? So this is r delta phi. Okay, so now if I know the length of the arc, and I know the charge per unit length is lambda, what's delta Q equal to? It's the charge per unit length times the length of our little piece of arc, right? Lambda is the charge density, linear charge density. So if I know how much charge I have over a certain length, and then I have a piece of a length delta S, I just take delta S, then I multiply by lambda. That tells me the charge. Okay, so therefore, delta Q is lambda delta S, but the arc length is r delta phi. And so we're going to take this delta Q expression and we're going to sub it in over here. Okay, so then E net is going to be the sum of all delta Q's on the ring okay, and then we just have to write in this delta Ez expression. So it's Coulomb's constant. Then delta Q, we're going to put lambda r delta phi. And then we have a z. And then we have divided by z squared plus r squared to the 3/2. Okay, so it looks like a complicated little expression. We, again, in the limit where delta phi is very small, we can express this sum as an integral. So for small delta z, the sum can be expressed as an integral. And it looks like the integral of Coulomb's constant, let's see, lambda r z, and then I'm going to do r squared plus z squared to the 3/2. And this is going to be an integral over phi. So if I want to go around the whole ring, the whole circumference, what range of phi values do I have to consider? 0 to 2 pi, exactly. So we're going to integrate over all possible values of the angle phi. Now, our ring has a constant radius. So r is a constant. Our point P is always the same height z above the ring. So z is a constant. Ke is a constant. Lambda is a constant. Everything in our expression is a constant. And whenever you have constants inside an integral, they can be taken outside. So let's take the constants, which include r and z, outside the integral. And so our E net would be equal to, let's see, Ke lambda r z divided by r squared plus z squared to the 3/2. The integral from 0 to 2 pi of d phi. So the integral of d phi from 0 to 2 pi, what it says essentially is add up all the small little angular steps until you go around the whole circle. So if I add up all the little d phis, what's the total change in angle? Well, it's just 2 pi. So all of this just evaluates to 2 pi. And so our net electric field is going to be, let's see, Coulomb's constant. And then I'm going to write it as 2 pi times r. In fact, let me write it as 2 pi r times lambda. Then there's still a z, and then there's a z squared plus r squared to the 3 halves. All right. So in fact, that's right. That's our final solution. But what is 2 pi r, the circumference of the ring, the total length of the ring, times lambda, the charge per unit length? If our ring has a total charge of Q ring, and its charge per unit length is lambda, and then I multiply it by the whole length of the ring, what do I get? 0. No, you get the total charge of the ring, right? So lambda is Q ring divided by 2 pi r. So therefore, 2 pi r times lambda is equal to the total charge of the ring. Okay, so that means this is Ke times the charge of the ring times z divided by z squared plus r squared to the 3 halves. And so this is 2 equivalent expressions for the electric field along the z-axis with a charged ring centered on that z-axis. Okay, so I'm not going to write this down, but let's just think about this. What would happen if we made z really, really big? So I'm going to take my point P and I'm going to move it further and further and further and further away from the ring, so that when I look at the ring, it looks like this tiny little circle, or in fact, it looks like a point little charge right at the origin of our coordinate system. In that case, we would want the electric field at point P, very far away, to look exactly like what we would expect for a point charge. So then we go back to this expression. What happens in the denominator if z becomes huge compared to r? How could we approximate z squared plus r squared? It should z squared. And then it's to the 3 halves power, so it becomes z cubed. And then we have z divided by z cubed. We would end up with 1 over z squared. And for large z, the electric field would be approximately Coulomb's constant times the charge divided by z squared, which looks just like a point charge as we would expect. Okay, good. Any questions about this example? Yeah. Yeah. It's probably supposed to be, I see what you mean. Yeah, you're exactly right. That should be a delta 5. Yes, you're right. Thank you. Okay, good. So I realized that these questions are harder, like the line charge and the ring of charge are more difficult than the standard problems that we do. But I wanted to show you this so that you could get the understanding. What I want you to take away from this is the way we treat continuous charge distributions is by thinking about what the electric field of point charges would be and then adding up the correct contributions. That's the real technique, okay? For anyone interested, we could use the result of the ring to calculate what we would get for an electric field from a charge sheet. So this is a bit of an aside here. So a charge sheet. What we could do is we could take a small ring and we would find its electric field at some point, Z, away from that ring. It's just given by, we just did it. We would take those expressions. And then we would say, okay, I'm going to surround that with a second ring. It just has a different radius. And then I'm going to take a third ring, and it has a different radius. And then I'll take a fourth ring, and it has a different radius. And I could calculate the electric field at point P due to all of these rings. But if I keep adding rings, more and more and more of them, I eventually will construct a uniform sheet of charge. So I keep adding the contributions of the electric fields due to charged rings, starting with a radius of 0 and going up to a radius of infinity, and I'll get a charge sheet. That calculation is a little more difficult, and so I'm not going to expect you to know it or to read it even. However, if you are interested, I put some notes on the course website that show you how that works. And it's very similar to the style of problem that we've been doing for the line and the ring. Okay, so there's some optional, not required, online notes if interested. Okay, good. So that finishes everything we're going to do with chapter 5, and that's the cutoff for the quiz number 1. I'm not going to ask you about a charge sheet, but the expressions for the charged ring and the charged line are on the formula sheet. All right, so with the last few minutes, what I'm going to do is I got a few questions, not tons, but I got a few questions about the last question on homework number 2. And so I'm not going to solve the whole thing, but I can set it up for you to show you how it works. So in this problem, we had 2 small identical conducting spheres. So first of all, it's important that it says conducting, because a conducting sphere, we can move charge from one to another, all right? And we're told that when they're a certain distance apart, they experience a repulsive force. Okay, so let's first just draw that. So the initial situation is that we have Q1. Let me call it Q1I for initial. And then over here somewhere, we have Q2 initial, and this distance is D. And what we're told is that the initial force is some value. Okay, so we're told that it's half a Newton in the version of the problem I got, but I don't care about the numbers. Okay, well, what we know from this setup is that the magnitude of the initial force would be just given by Coulomb's law. So it's Coulomb's constant times the product of charges divided by the square of the distance between them. All right, good. So then what we're going to do is we're going to connect these 2 charges with a wire. Some charge will go from, whichever one has the bigger charge, some of that charge will leak off and go to the second sphere. These 2 conducting spheres are identical in size. So what's going to happen to the charge when they're connected by the wire? How will the charge of the left and right spheres compare when we connect them with a wire? They'll be equal, right? The idea is that the sphere with more charge, those charges have a stronger Coulomb repulsion. So if they have the option to go over to the second sphere that has less charge, they'll do that because they'll experience less of a repulsive force. So in the final situation, we're going to have our two spheres. So we'll call Q1 final, but I'm just going to say that's equal to Q. And Q2 final is also equal to Q. So the charges are the same after they're connected by the wire. This is still D. And so now we have a new repulsive force. Let's call this F final, like so, F final. Okay, so F final is going to be Coulomb's constant times the charge of sphere 1 times the charge of sphere 2, but those are both equal to Q. So that's just Q squared divided by D squared. So this, let's call this 1 and let's call this 2. All right, now there's a problem that we have here. The problem that we have is that we have three unknowns. We're not told the initial charge of either sphere. So we don't know Q1 initial or Q2 initial, and we don't know Q, the final charge of the spheres. If we have three unknowns, we need three equations. We have only two of them. So the other bit of information that you need is that the total charge of the system does not change before and after the wire is connected. So the total charge of the system remains fixed, right? We're not adding charge or removing charge. We're just allowing the charge that's already on the spheres to maybe redistribute. And so that means that Q1 initial plus Q2 initial is the total charge before the wire was connected, must be equal to the total charge after the wire connected. It's just Q plus Q is 2Q. And so this is our third bit of, in fact, let me rearrange this and say, therefore, we could write 2Q initial is 2Q minus Q1 initial. So we'll call that equation 3. And then now we have enough information to solve this problem. And the easiest way to do it is to recognize that, well, in fact, equation 2 is a really simple one. We know everything in equation 2 except for Q. We're given the final force and we're given the separation distance D. So the steps are to first use 2 to find Q. All right. Step number 2 is to take equation 3 and sub it into equation 1. The problem with equation 1 is that it has two unknowns, Q1 initial and 2Q initial. So what I'm going to do is I'm going to use equation 3 to get rid of the unknown Q2 initial. So we're going to sub 3 into 1 to eliminate Q2 initial. All right, and so when you do that, you're going to end up with a quadratic equation for Q1 initial. From step 2, you end up with a quadratic equation for Q1 initial, and you could solve that with minus b plus or minus the square root of b squared minus 4ac over 2a. So you just find the coefficients and solve that quadratic equation. In fact, that's the end of the problem. Your quadratic equation is going to have two solutions. One of them is going to be Q1 initial. What's the other one going to be? Q2 initial. Okay, so that's that last problem in homework number 2. All right. Thanks very much. Yeah. Yeah, I just auto programmed it in. So like even on the even for like